Hi everyone, we are Team 5 and our project is about building EEG models for cross-subject generalization. You've probably seen EEG waveforms before, but here's the surprising part. Two people doing the exact same task can produce majorly different temporal brain signals due to a lot of external factors and noise. Models can latch on to these differences and that's why they fail on new subjects. With non-invasive EEG signals, this cross-subject variability is a fundamental bottleneck. Temporal features change too much from person to person, causing models to overfit. But our analysis across datasets shows something interesting, that spectral features are better and more stable than temporal ones. Frequency bands stay more consistent across subjects, which makes them a stronger foundation for generalizable decoding. Most prior models like EEGNet and CLT operate on the temporal domain, so they can inherit that instability. We have built models in the spectral domain and enhanced them with SE blocks, which is a lightweight attention mechanism. Now let's look at the dataset and approach we have used.
For our project, we use 4 standardized EEG benchmarks sourced from the multi-DiffNet paper, which is one of our baselines. These are increasing in difficulty to ensure our model can adapt to different tasks. This figure shows the different classes and subjects across these datasets, and they have distinct pre-processing parameters for the raw signals. They're split into training, validation, and 2 test sets, which include seen subject split and unseen subject split. With that, we introduce our solution, ScaleNet, which is Spectral Convolutional Attention LSTM Encoder Network. The main improvements are that we're using spectral data and also using the SC block, which is our attention mechanism. This is our model architecture, which first involves turning the raw signal into the spectral domain using STFT. Then it is reshaped and fed into 2 blocks of convolutional 2D layers, followed by batch norm and the SE block. The SE block brings more attention to the important and informative spectral features, and it involves first step, which is squeeze, which does the global average pooling, then excitation, which does adaptive learning, and scale, which is the reweighting step. Then it is passed to our LSTM layer and our fully connected layer to get our classification prediction. Additionally, we use cross-entropy loss function shown here to minimize the difference between the true and predicted classes.
And we use unseen subjects accuracy for evaluation metric. It measures model performance on data from new subjects not in the training set. The purpose is to assess robustness against individual neural variations and noise. And this slide shows baseline model performances using EEGNet, EEG transformer, and multi-DiffNet across tasks. We can check EEGNet shows highest performance for SSVP P300 MI dataset, and multi-DiffNet shows highest performance for image speech dataset.
Now we evaluate ScaleNet on the same dataset. From the SSVP test, ScaleNet achieves an unseen accuracy of 91%, outperforming all other baseline models. However, for P300, MI, and Imagine Speech, its performance is lower than the baselines. This means that ScaleNet works well only for specific tests, and improving its robustness across different paradigms remains an important challenge. Although our current architecture uses the SE block for attention, we plan to explore alternative blocks such as residual blocks and CPAM to further performance across all tasks. In addition to improve model interpretability, we applied GradCam and compared the activation patterns for correctly and incorrectly classified trials to see how the model's focus changes between right and wrong predictions. Our next step is refining model to improve results for all datasets, like optimizing parameters, try different sampling rates, or we can try other attention mechanisms and try integrating SE blocks directly into multi-DiffNet, which is one of our baseline models. These are our references, and thank you for listening to our presentation.